come over and sit down. Lorrin, over to you. Let's just show appreciation as we welcome him.
Oh, can you hear me in the back okay if I speak about this level? Yes, no? Can you hear me? Yes. Louder? Okay, I'll try and shout a little bit. Well, in the Sunday school class taught by Greg Porter, the one what I'm in, we talked about the stewardship of time for about the last month. So this leads into what time is at this point, and we'll see how things go. Yeah, I think you'll find this quite fascinating. But first, a few caveats. To describe time, we must use a little physics. Sorry, folks, but I'll keep it simple. The KISS principle. Keep it simple, stupid. To discuss physics, there's math. Just a little 8th grade algebra, no more, no calculus. But physics without math is like spaghetti without sauce. But we're going to have a little linguine and a little olive oil with cheese. But of course, when you simplify things, there are inaccuracies that invariably come along, and you get less than a complete picture. In other words, I'm going to tell a few white lies as we go along here. This is a very well-known, famous part of Scripture about time. For everything there's a season, a time for every activity under heaven. A time to be born and a time to die. A time to plant and a time to harvest. And it goes on for several verses. Yet God has made everything beautiful in its own time. He has planted eternity in the human heart. Eternity, a long, long time. From Galatians, so let's not get tired of doing what is good. At just the right time, we will reap a harvest of blessing if we don't give up. The word time appears about 600 times in the English Bible, depending on which translation. Time is all over the place in the Scriptures. Now, there are two very different questions I want to pose. What's the time? We say this every day. 10:30, 11:30. What is time? Now, that gets a little bit more complicated. Let's look at some common definitions of time. The thing that is measured in seconds, minutes, hours, days, years. And those little blue globes you see on there, those are hypertext links to other information. They're like footnotes. There are probably about 100 of them in here. The continued sequence of existence and events that occurs in apparently irreversible succession from the past to the present to the future. Okay. Then we come to this gentleman, St. Augustine of Hippo, a very wise man. He was a theologian and a philosopher. What did he have to say about time? There you go. But thanks to Google Translate, what is the time? If one asks me, I know. If I want to explain it to a questioner, I do not know. Smart guy. So what is time? Concept of time is challengingly complex, as you will see. But I promise to keep it simple. Time is relative. It's not absolute. In other words, the time depends. 11 o'clock in Virginia is 8 a.m. in California, 11 p.m. in Australia. In this case, it depends on longitude. Time is influenced by speed and by gravity. Now, these latter two things impact our daily lives. You may not realize it, but you'll see. Time is associated with change. Days, months, seasons, years, lifetimes. Stars moving in the sky. The moon going around the earth. The earth circling the sun. Tick-tock, tick-tock. All clocks have a tick-tock. And the faster the tick-tock, the more accurate the clock. We have calendars, the Gregorian calendar, which is accepted worldwide today. It's the de facto standard. This was introduced in 1582. There's a Chinese calendar, an Iranian calendar, and a whole bunch of religious calendars. And here's a universal calendar. Depending on which calendar you're picked, there are 12 different dates for the new year. It's a mess. Let's go back to the Gregorian calendar. A year is the time taken by the earth to revolve around the sun. 365 days a year? Well, not exactly. We were aware of leap years. 365.25, well, still not exactly. The average number of days in a year is 365.242374. Sorry. 97 out of 400 years are leap years, not 100. That's to account for this very weird number. 4 seasons each month, the meteorological seasons, which is what we normally use: spring, March, April, May, summer, fall, and winter. It's particularly important, especially in northern latitudes, to know about spring and when it starts, because that's the time to plant. If you miss it, you may starve to death. It's a critical point. There are astronomical seasons which change every year. Spring, March 19th this year, it's called the vernal equinox. Summer, summer solstice. Fall, autumnal equinox, and winter is coming starting December 21st. Equinoxes, just remember the day and night are equally long. Equinox equal. Same amount of darkness as light. The solstice, the shortest and the longest days of the year. Here's the pyramid of Kukulkan, which is in Yucatan, Mexico, and was built sometime between the 8th and 12th centuries. Now, notice that wiggly line. What did I do with my pointer? Right here, the shadow. That occurs on the spring and fall equinoxes, only 2 days a year. Pretty clever building. Imagine that time knowing when those dates start. This is a Newgrange in Ireland. It's kind of a half a cave, a half a building from 3200 BC. And on the sunrise, on the winter solstice, for maybe 15, 20 minutes, you have that shaft of light, just once a year. And then we have a modern-day Druids celebrating the summer solstice in Stonehenge. Past the Budweiser, this is a big party going on. Or since these are Druids, it's probably past the mead. The months, we all know those. Oh, sorry. Yeah, that's right, the months. There's the old jingle, 30 days, half September, all the rest I can't remember. So what is written in the Bible about time? Pastor Daniel wasn't around when I wanted to answer this question, so I turned to artificial intelligence, Microsoft Copilot. And I asked the Copilot, what is written in the Bible about time? And here's the answer. Now concerning how and when all this will happen, dear brothers and sisters, we don't really need to write you. For you know quite well that the day of the Lord's return will come unexpectedly like a thief in the night. From Thessalonians. Not only did it pop up this verse, it gave an explanation. The Apostle Paul addresses the Thessalonian believers. He acknowledges that there's no need to elaborate extensively on the specific time and dates. Instead, he encourages them to remain vigilant, watchful, and prepared for the Lord's return. Pretty good, pretty good. And if you notice in this verse, there's no word time. It's a concept that was translated into this. Clocks are needed to tell time, clocks of one kind or another. Let's start with a sundial. This is a picture of the actual sundial in a museum in Cairo, and you would put a stick there which stands out vertically. And the shadow from that stick goes clockwise. And now you know why analog clocks go clockwise because the shadow goes like that. Now, when the sun doesn't shine, it's not very helpful. So the Egyptians had a water clock. And when you filled it up to here, there's a hole down at the bottom. And water drip, 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 drip. And as it gets down here, it's drip, drip, drip. So it's not a linear change. The Romans solved that problem. Here's a water clock, a picture of one. There's a water supply that drips into a reservoir here, and it drips fast here, and it overflows. So it's always a constant head of water pressure. And then the water drips down into this reservoir where there's a float, and the float goes up as the reservoir fills, and it has a cog that drives and moves a hand. So even if the sun doesn't shine, you can tell the time. Here's a modern day water clock. The time displayed is 4:06. If you look here, you'll see 4 bulbs, colored water that are filled. Those are the hours. And on the other side, there are 3 bulbs that are filled. So every 2 minutes, one of these bulbs gets filled. 4, 2 times 3 is 4:06. This is the Salisbury Cathedral clock, which was installed around 1386, the oldest working mechanical clock. Well, I put oldest in quotes because if you travel around Europe, you go to these little villages, invariably you'll see the oldest clock in the world in a tower in this little village. Here's the clock tower in Passau, Bavaria. I've got too many things going here. Passau was not bombed or shelled during World War II, so that clock really is the original clock that was put up in the 14th century. There's a river here. There are 3 rivers that run through Passau. One of them is the Blue Danube, which is usually rather brown. This is the first spring clock, again, first, from about 1430, and it was given to this gentleman, Philip the Good, Duke of Burgundy. Philip the Good actually was not a very good guy, but he looks very nice and pious here, and he liked his clock. This is the first pendulum clock. It was, it was patented by Christian Huygens in the Netherlands. This now looks quite familiar. We see pendulum clocks around all over the place. Here are 3 grandfather clocks from 1700, 1750, and modern. They all work on the pendulum. And the pendulum clock can be very accurate depending on how you manufacture it. Now we're going to shift to a little geography, some navigation, and of course time. Now navigation at sea with a sextant before 1760 worked, but it was a problem. It wasn't easy. Latitude, easy peasy. All you have to do is get the angle of the North Star, and just a quick calculation, you have the latitude. I'm simplifying this a little bit, folks. And then if you take a noon sight with the nautical almanac, you can figure out the latitude quite easily. Determining longitude is another issue. Even with the sextant, it's challenging. It certainly can be done. It was done for hundreds of years. But it's complex without an accurate clock. Noon sights with an accurate clock, easy peasy. No problem. Today with GPS, you have instant, accurate, and continuous position to a fraction of a second in position. How many people have a GPS in their car? Okay, a little geography. These are the Isles of Scilly, not the Scilly Islands, the Isles of Scilly. They're off the coast of Cornwall. They're on the approaches to the English Channel. They're not tropical, but you see palm trees there. It's quite amazing. And they grow a lot of flowers that are then brought over to the mainland. This is what the Isles of Scilly look like from the International Space Station. They are a hazard to navigation. And there's a very famous lighthouse out there called the Bishop Rock Lighthouse. It's been there for a long time. Here's the latitude and longitude of the Isles of Scilly. 49 degrees north, meaning it's 49 degrees north of the equator. 90 degrees north is the North Pole. It's 6 degrees west. West of what? Ah, I heard Greenwich. Yeah. Okay, now we're going to talk about time and longitude. There is the prime meridian that runs through Greenwich. Greenwich is a suburb of London. It's downstream in the Thames, I don't know, 8, 9, 10 miles. You have 180 degrees west of Greenwich and 180 degrees the other direction of Greenwich for 360 degrees. If you divide 360 degrees by 24 hours in a day, you get 15 degrees per hour. Now, you're on a ship out here somewhere, and you find out when the sun is the highest in the sky. That's noon, by definition, where you are. And then you look at your chronometer, which was set at London, and your chronometer says it's 1 o'clock. So that means you're 1 hour difference from London. And 1 hour difference means you are 15 degrees longitude. Simple. Oh, but one other thing I wanted to mention. We are at 77 degrees west longitude here. If you divide that by 15 degrees, that means London is 5 hours difference. Yeah, it is. It's 5 hours later in London. Now, the prime meridian. Here it is. It's at the Greenwich Observatory and Museum in Greenwich, except it's not quite there. This was laid down in 1960, and since then there have been refinements, more accurate, and it's about 300 and some odd feet to the east. So if you use your cell phone, it won't read 0 degrees longitude and you're standing there. So we come to a disaster at sea. This is in 1707. 4 Royal Navy ships ran into the Isles of Scilly, literally. They ran into them and sank. There were, I think, about a dozen ships. A number of them escaped. They were on their way to Portsmouth, England, but 2,000 lives were lost. So this was about 230, 40, 50 years before Titanic. Most people don't know about this wreck. The cause is bad weather. They couldn't navigate, and they didn't know where they were, particularly in longitude. 7 years later, the British Parliament passed the Longitude Act. There was a prize for finding a practical method to determine longitude at sea. You can't use a pendulum clock because ships pitch and they roll and they corkscrew and the pendulum just goes all over the place. The reward is £20,000 or about $4.4 million in today's money. Big prize. Along comes this gentleman, John Harrison. He's a carpenter. What does a carpenter have to do with clocks? Glad you asked. Here's a clock that he made. It's made entirely of wood. It's made out of oak and lignum vitae. Lignum vitae is a tropical wood which is quite oily. So the parts that needed lubrication, he made out of lignum vitae. This clock is still running, and it was put out around 1722. So then Harrison turned to making 4 more clocks that I'll show you. They're at the museum in Greenwich. They're now all made out of brass and other metals. They're fascinating to watch. They're still running. You can watch them go tick-tock, tick-tock. This is the H1 from 1735, H for Harrison. This is the H2, the H3. He was just never satisfied. And finally this one, which doesn't look like the others at all. This looks like a big pocket watch on steroids, and it weighs about 3 pounds. Incidentally, well, 1 minute, I'll get to that. The accuracy is minus 0.11 seconds per day. So if you set that clock in Greenwich at the correct time, It'll only lose, not plus or minus, but lose 0.11 seconds per day. This is a $20 Timex I bought 10, 12 years ago. It loses 6 seconds a year. 0.11 seconds per day is about 40 seconds per year. So this $20 plastic watch outbeats this. On a voyage to Jamaica in 1762, the ship's position was only off by 1 mile, which is incredible navigation. And now we have Harrison, the gentleman, with the H3 up here, and the marine chronometer down here. You can still buy ship's chronometers. I'm not sure why anybody would buy one anymore, but you can buy them. They're gimbaled. That means the clock stays steady as the ship pitches and rolls. Typically, they're accurate from minus to plus 6 seconds a day, and you have to calibrate them so you know after so many days what the correct time is. Mechanical movement, and $4,000 for these things. They're a curiosity piece, really. Everybody knows Big Ben. That clock weighs 5 tons, and it loses plus or minus 2 seconds a week. They reset it every week. It's now called the Elizabeth Tower clock. Now we come to a modern quartz wall clock. You can buy this from Amazon for $10. A typical quartz wall clock, or any quartz clock, will lose or gain 0.1 to 0.2 seconds per day. That's a minute a year. Not bad. Now, how does a quartz clock work? There's literally what looks like a tuning fork in the clock. And it hums along at 32,768 cycles a second. Tick, 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 tick. Really fast. You can't hear it. Humans can only hear it about 20,000 CPS. We older folks don't even get there. Now, if you take a watch like this and pry the back off of it, this is what you see. There's a battery, a quartz crystals in a little tube, a counter. It's just a printed circuit, very simple circuit that counts the cycles, and every time 32,000 go by, the second moves. And there's a stepping motor to move the hands. It's very simple. Now on Amazon, they advertise atomic clocks for sale. They are not atomic clocks. They're radio clocks. Although they say atomic clock on them. How they work was they detect a radio signal that comes from Boulder, Colorado, 60 kilohertz. It's a time signal from an atomic clock. And every night it updates the time on this so-called atomic clock. They're fairly cheap. Atomic clocks are a little more expensive. Now, anytime you mention atomic or nuclear to anybody, the general public, what do they think? Yeah. How many of you have had a MRI scan? I see all these oldies in here. You know, you go in there and it's whir, buzz, click, click, don't move, buzz. The technology that's used in that machine is called nuclear magnetic resonance. But the medical community said, we can't use the word nuclear. We'll never get anybody in one of these machines. Nuclear magnetic resonance, NMR, has been around since 1940. It's a form of spectroscopy, NMR spectroscopy. It's used in chemistry and physics all the time. So this is the first atomic clock from 1949. Professor Isidore Rabi at Columbia University built it. He won the Nobel Prize in 1944 in physics. Not radioactive. So I'm going to run quickly through the history of atomic clocks. The first cesium atomic clock is called NBS-1, NBS, National Bureau of Standards. 1952. The first commercial one you could buy for about $200,000. came along in 1958. NBS 4 in the 1990s. NBS 6 with an accuracy of plus or minus 1 second in 300,000 years. Not bad. NBS became NIST, National Institute of Standards and Technology. I can't remember when that occurred. NIST is up on Highway 270 in Gaithersburg. If you go northwest, it looks like a university off to the left side. So the F1 came along in 1999 with an accuracy of plus or minus 1 second in 20 million years. F2, which was in service from 2013 until now, plus or minus 1 second in 300 million years. The F3 is under development. The F4, they're looking at it. And there's a new kid on the block called Thorium-229 clock. It's a nuclear atomic clock. It's under evaluation, which will be even more accurate. So here's a picture of the F2. Doesn't look like a clock at all, does it? NIST also makes available a miniature atomic clock. And there's a coffee bean right next to it to get an idea of the size. Now, how does a cesium clock work? Well, when you zap cesium with a microwave, the electron in the cesium's outer shell wiggles back and forth. It tick, 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 tick. And it goes between two states. It's called a hyperfine transition in science speak. But in other words, the thing moves back and forth at 9,192,631,770 cycles per second. You can't hear that one either. This transition doesn't change. It's not affected by temperature, pressure. It's constant. And the transition can be measured very accurately, which leads to a very accurate clock. This is a strontium atomic clock. So instead of cesium, it's using strontium. It's a co-project between NIST and the University of Colorado. Its accuracy is plus or minus 1 second in 15 billion years. But now we have optical clocks. A lot of research is going on in this area with an accuracy of 1 second in 50 billion years. You don't have to set this very often. And you can now buy optical clocks. I didn't look farther than that for the price. We're not going to be buying these things. Now it's time to talk about UTC. And I need to look at my clock here. Okay. UTC is a worldwide accepted time. Even the US uses UTC. And it is calibrated by using 400 atomic clocks spread all over the world. They all come into sync. And everybody agrees that this is the time. UTC replaces what used to be called GMT, Greenwich Mean Time. It's now UTC. And there's a lot of information on the web about this if you're interested. You can buy cesium atomic clocks. Here are 3 companies that sell them, and they typically are $2,000 to $3,000. You can even buy a wristwatch. Now, Amazon used to sell these things. I checked a few days ago, and I didn't see it. But you can buy them from a company in Hawaii, just $6,000. Now, if you wear that clock, you are a true geek. A lot of information about atomic clocks is available. Now, time to turn to the second. The second is the standard unit of time. It's not an hour or a minute. We've all gone through this routine, right? If you want a slower clock, it's 1 California, 2 California. The standard is when the electron of a cesium wiggles 9 billion blah, blah, blah times a second. That is what is the accepted second. Tick-tock, tick-tock. To put it into scientific speak, The second is equal to the duration of 9 billion blah, blah, blah periods of radiation corresponding to the transition between hyperfine levels of the unperturbed ground state of the cesium-133 atom. And you thought lawyers were bad. Now we need to look at the speed of light. This is relevant to time. The speed of light is 299,792.458 kilometers a second. Let's just call it 300,000. Keep it simple. That's 186,000 miles per second. That's, it's pretty fast. I'm not going to go through the whole history of determining the speed of light. The first one to try it was Galileo, way back in the 1600s. But the technology at that time just wasn't up to it at all. But people sense it. How fast does light move? Well, the conclusion was in 1983, the scientific community said, okay, that's enough of this. We've looked at this for hundreds of years. We can determine it very accurately. We're now going to say it is 299,792.458 kilometers a second. So that is the worldwide accepted speed of light. Now, the speed of light in translucent substances is different. Now, 300,000 kilometers a second in a vacuum. In water, it slows down to 225,000. In glass, 200,000. In diamond, only 125,000 only. But what happens after the light exits this substance, it goes back to 300,000. I'm not going to take the time to tell you why. It's just weird. Now, the speed of light in the atmosphere is slower because of refraction. And that is important. In the atmosphere, light moves at 1.003 times slower. And that is the index of refraction. That's the definition of index of refraction. Now, a little kitchen physics. You can really wow your grandchildren doing this, or the younger ones, their children. All you need is a microwave cavity, and you have one in a microwave oven. You need some marshmallows, small ones. You need a plate and a ruler. That's all you need, and you can determine the speed of light. Now, if you don't have a metric ruler, 2.54 centimeters per inch. You need to know the frequency of the microwave oven. Typically, it's 2450 megahertz, or a big number hertz, cycles per second. That'll be on a plate on the back of the microwave. And there's a simple formula. The speed of light is equal to lambda times f. Lambda you get from a measurement. You put the marshmallows evenly on the plate, put it in the microwave, and you don't want it turning. Your microwave, and you'll see marshmallows melted here and marshmallows melted here. The difference between where they melt is the wavelength. You plug it into this formula, and lo and behold, you have the speed of light. Wow the kids. Lots of information on the web to do this. Okay, a minor distraction here. Some questions. What time is it? How fast are we going? Speed, how fast we're going, is distance divided by time. 60 miles per hour. We all know this one. How about distance? Distance is speed times time. If we go 60 miles an hour and travel for an hour, we've gone 60 miles. So remember, distance is speed times time, okay? You've got to remember that. How can we find out where we are on Earth? What is the length of the American foot? The foot is related to time. I'm going to show you. There was an act of Congress in 1866 which legally protected the use of the metric system from lawsuit. Isn't that weird? What was happening is Company A was suing Company B if they used the metric system, just to try and get money out of the Company B. I mean, juries were saying, oh yeah, you can't do that. We only use feet in America. You can't use the metric system. So Congress said, enough of this nonsense. At the same time, they provided official table for customary units, all based on the metric system. This was in 1866. Since 1893, the American foot has been defined as 1,200 divided by 3,937 of a meter. Our foot is defined in terms of a meter. And indirectly, we've been using the metric system ever since. Now, what is the length of a meter? The meter is defined in terms of the speed of light. The speed of light is 299,792,458 meters per second. If you take the reciprocal of that, flip it upside down, the meter is the length of light traveled in a vacuum in that fraction of a second. That's how meter is now defined. Simple. Really, it's simple. Speed of light, flip it upside down, you've got a meter. The worldwide uses 7 basic standards. Everybody. It used to be that Liberia and Myanmar, along with the U.S., didn't use the metric system, although we really did. But Liberia and Myanmar now use the metric system. We're the only holdout in the world. But anyway, these 7 standards are all based on natural phenomenon. The last one was the kilogram. But these natural phenomena don't change. You can measure them more precisely, but they don't change. Also, you have to use 5 fundamental constants, which I'm not going to even talk about, but they are calculated to a very high degree of precision. So the whole world now is based upon natural phenomenon. Anything that has atoms in it or any type of energy can be described and measured in these terms. Okay, back to time. Now, how many have used your GPS in the car? Yeah, okay, almost everybody. Let me talk a little bit about global navigation systems. The U.S. started in 1995 for military use only. But in 1983, there was a tragedy. The Russians shot down a Korean commercial airline that had strayed over Russian airspace. And at that time, the actor Reagan, thank you, said enough of this. We're going to release this for civilian use. Also in 95, the Russians deployed GLONASS. The Big Dipper from China has arrived in 2020. The European system went live last year. Japan and India have regional systems, but they will go international probably in the near future. So there are a bunch of them. All these systems use time to function. That's the key. Our system, GPS system, 38 satellites, and 32 are operational at any one time. They are in orbit 12,552 miles. They go around the Earth twice a day at a speed of 8,724 miles an hour. Each satellite contains 4 atomic clocks. That's the key. Each satellite transmits continuously the satellite's ID, orbital information for that satellite, orbital data for all the satellites, and very precise time information. It sends time. The satellite's times and the speed of light gives the distance between the GPS unit in your car for each of the satellites. If you have 3 of them, you'll know where you are. If you have 4 of them, you also know the altitude you're at, the speed, and the direction of travel. That's why the little car on your GPS moves. So it is dependent upon sending time information. Now, the accuracy of common GPS devices, cars 10 to 50 feet, smartphones, your cell phone, plus or minus 16 feet, handheld GPS units, plus or minus 10. Military systems, 3 feet. Now, the military systems take into account the refraction of the atmosphere, so they're more accurate. But I think in reality, fixed systems are known to the military within millimeters. Real-time kinematic GPS systems, plus or minus 1 inch. If you see people out surveying on roads, you see all kinds of instruments on tripods. Those are this type of a unit. So they can get it within 1 inch. Now, things get unintuitive, but this really impacts our daily lives. Let's compare 2 atomic clocks. One on Earth, here you see it sitting down here, and another one in a satellite. In 4,575 years, the satellite clock will be 1 minute ahead. Crazy, isn't it? What do you care? What difference does it make? I'm going to tell you. This is called time dilation. It's the difference in elapsed time between 2 clocks. And for example, one on a satellite and one on Earth. Clocks will show different times due to the difference of speed. The satellite one is going around like this. The fixed one on Earth isn't moving. And this is in response to Einstein's special relativity. Einstein published a paper in 1905, this one. In fact, if you click on that, you'll get the original German picture or article. And this is an English translation. So what Einstein says, that time is dependent upon speed, and it's also dependent upon gravity. Clocks will show a different time because of gravitational effects. There's a much lower gravitational potential in that clock in the satellite than there is on Earth. And again, this was published in 1915, German and English. These are heavy reading. Now, consider a clock in a satellite and another on Earth. The satellite clock will lose 7.27 microseconds each day. There are 1 million microseconds in a second. I know, your eyes are glazing over. The satellite clock will gain 45.61 seconds each day. You have to account for this. The net effect is the clock and the satellite will gain 38.34 microseconds per day. Now, here's the formula for calculating the effect of speed. 8th grade algebra, but if you can't hack it, there's a website that you plug in the numbers and it'll do it for you. For gravitational effect, this formula, again, 8th grade algebra, but you can do it on the web. Just plug in the numbers. Now, what happens if you don't correct for these time changes? The GPS location will be meaningless after several minutes. Never mind a day. The air and positioning would accumulate to about plus or minus 6 to 12 miles per day. 200 to 450 feet after 5 minutes. So you think you're on Oak Street and you're on Maple Avenue. A ship traveling in the shipping channel to Baltimore has a 700-foot wide channel. After 10 minutes, you're no longer in that channel and you're knocking down a bridge. Now, that's not what brought down the Francis Scott Key Bridge. But this is what you have to do to make sure your GPS works accurately. You have to account for gravity and speed. So if we have here 2 generations of clocks that were used for navigation. In 1759, the Harrison's chronometer. Now you can use this in place. Or a cesium clock, which really nails it down very precisely. I listed some potential reading here. The book Longitude is really a great book. You don't have to know anything about science. It's a fun book to read about Harrison and his clocks and longitude. These two, well, that's for the scientists and the engineers in the crowd. There's a lot of math in them, but they're very good. Look carefully then how you walk, not as unwise, but as wise, making the best use of time, because the days are evil. Teach us to realize the brevity of life, so that we may grow in wisdom. More time. Can all your worries add a single hour to your life? Matthew, more about time. 586 more verses to go, so time to stop. So thank you very much.
Thank you so much for elaborating on time. I think we all take time for granted, and particularly if you come from my part of the world, or in Africa, time is just all over the place. Nobody takes care of time, not here. So I think this is really important for us. So I'm going to open the floor. You may have some questions, particularly our young people who are here. I'm pretty sure next time we do this, we're going to open it up to our community, because this is really fascinating. So if there are any comments or questions, you got some mics on your table. I will be happy to bring this mic to you. Anybody for Lorrin? Any question?
Okay, I found it. Oh, hi. Okay, so the first verse that you brought up, I think it was from Ephesians, and it said, time is evil. What's the context for that one?
Ephesians. That was Paul writing. No, I'm not sure.
Yeah, I'm just curious about time is evil.
I think Pastor Daniel would know.
Please.
Sure, I will be glad to explain what I know about that question. I think Paul wrote to the church in Ephesus, and that was a very difficult time for the church. There were all kinds of persecution going on, and Paul wrote to remind them to make the most of the time that they have. You know, if you actually go back to the beginning of the Christian church, particularly in the book of Acts, the church actually began in the midst of persecution and suffering. You remember the first Christian martyr, Stephen. When he was being killed, Paul was there, and he was encouraging them. And then later on, Paul himself became that, person who was persecuted. And so these times are evil was actually written to them to make the most of time, which actually jives or agrees with, what you're sharing with us, that we need to make the most of the time that we have, because we don't have all the time in the world. So, it was in the midst of persecution when that verse was actually made.
Thank you.
I just had a question. Is time a more human concept or more of a scientific concept?
I think it's both. Both.
And if it's a human concept, then why are seconds the only solid measurement that we can all agree on? Since different societies would mostly want to have their own measurements of time throughout the ages, why are seconds the solid foundation of time?
Well, you would agree you have to pick something. something. You have to pick one thing to make as a standard. In pre-industrial age, people really didn't worry about seconds or even minutes. They worried about sunrise and sunset. That was really the period of time. But some measurable thing has to be determined as the standard, and then you can derive all the others against it. And the scientific community picked a second to do that.
That makes sense. Thank you.
Any other question? We got about 5 minutes, so we don't want to conclude this. Yes, Larry.
First off, when we look at our cell phones and we see the time that's there, where is that coming from? And then secondly, when we talk about these atomic clocks that are accurate for 1 billion years or 2 billion years. How do we determine that accuracy, since it's something we can't tell in our lifetimes?
Yeah. To answer your first question, I'm in trouble here. The answer to your first question is, I'm going to get some water here in a second. Gives me time to think. Oh, thank you. Okay. Let's see, your questions were, the first one was, oh, it's cell phone. The cell phones times are synchronized with the clock that comes from Apple, for example. That's continuously sent out to your phone. The clock that Apple sets each night is from an atomic clock. So the clock on your cell phone may be off a fraction of a second, but that's about it. The answer to your second question was, how do they know it's 50 billion years? What is done, let's say a dozen clocks are set up to have the exact same time. And over the period of, let's say, 6 months, there will be differences of a microsecond between a couple of them. Then statistically what you can do is with these dozen clocks and that slight deviation that occurs over 6 months, 12 months, you can then estimate what the average clock will be in a certain period of time. So that's the way it's guessed at, if you will. Yeah.
Well, thank you so much, Lorrin. Let's just show our appreciation again. Time is up. One of our pastors was telling me, I think we need to open this up to advertise this next time we actually get you to do this for us again on another important topic. We're going to open it up so that we can get more people within our community to come in and listen to this. So I'm going to conclude with prayer. The conversations will continue. You know, he's still around. The good thing is he's one of us. So you can always get him and ask him questions. Go to the Lord in prayer with me. Father, we thank you for the concept of time. You transcend time. And we thank you that with you, Father, we can come to you no matter what, whatever time it is in our lives. You're always there for us, the constant. And so thank you as we continue to consider and ponder and reflect upon this important gift you've given us. And again, as Paul wrote, so that we will be mindful and conscious of the time in which we live. Bless us now as we transition to our time of fellowship and interaction, and as we prepare for our worship service. Thank you for Lorrin, for his guidance and his wisdom. We ask and we pray through Jesus Christ our Lord. Amen. Thank you all. God bless you.